So in the last video, early on in the video, we looked at how we can find the graph of the derivative or the second derivative from the function. But now what we're going to look at is the first derivative test, which will show us how we can get certain aspects of the graph from a certain number. So if we were looking for a max or a minimum at a certain number on the graph, we would need to do the first derivative test. So I'm going to take a function as an example. So f of x equals 1/3 x cubed minus x squared minus 3x plus 3. So then f prime of x would equal x squared minus 2x minus 3. Now, to the first derivative test, we need to get the critical numbers of the function. And to do this, it's just getting the zeros of the function. What does x equal to make the function 0? Because that is when you have your max or your minimum. So now we just need to do this out by using simple algebra. So we would factor this. So that would come out to equal x 0 equals x minus 3, x plus 1. So your zeros are 3 and negative 1. So what you do now is you set up a derivative chart. So you set up your derivative chart, your first derivative chart, and you already know your zeros because you have 3 and negative 1. So you have x and then f prime. So you know at negative 1 and 3 it's 0. So we would want a number less than negative 1, which could be negative 2, a number greater than negative 1 and less than 3, which would be 0, and then a number greater than 3, which would be 4. And when you plug these back into the equation, negative 2, you get a positive. When you have 0, it's negative, and for 4, it's positive. So when you look at this, what this tells you is it goes from positive to 0 to negative, which means that you have a max at negative 1. And it goes from negative 0 to positive, which means you have a min at 3. And that is how you use the first derivative test to find the max or min of your equation, of your function.
So now that we've seen an example of the first derivative test, we're now going to show an example of the second derivative test. So we're going to start with a function. And that function is x cubed minus 12x minus 1. So we're going to find the first derivative of that, and we know how to do that through our power rules, and that's 3x squared minus 12. So we're going to get the critical numbers for this still like we would in the first derivative test. So we're going to get x equals positive and negative 2. So we're going to take the second derivative of the first derivative, and that is 6x. So we're going to take the critical numbers that we found from the first derivative and plug them in as x in the second derivative. So 6 times 2 equals 12, and 6 times negative 2 equals negative 12. So the actual number doesn't really matter, but the value of negative 12 is less than 0, which means that it's concave down, which is on a function, if we were to graph that, concave down would be a max. So that's a max at negative 2. And because that's positive, it's the opposite. That is a min at 2. So we know that it's going to go from at negative 2 like this, and then at positive 2 like this. So this point right here is between negative 2 and 2, and that point is going to be 0. So we know that there is a point of inflection at 0. And if we want to plug it into the chart, which we do, and we plug these numbers in to the second derivative equation, which is 6 times, sorry, that's supposed to be not a 0, a 1. That'll be negative 0, positive, which means the graph will look like this. And that is it. So now we're going to talk about optimization problems. Optimization problems use derivatives in a way that will optimize the results. So we're looking to get pretty much the best results that we can while doing these problems. So there's so many different ways that you can use optimization problems, but we're just going to show an example of one. So we're going to give some of our given information here. So this is some of the information that we know. Okay, and we're going to draw out the box here. Now the L lengths, are the same. This is a box here. So we know that it's a square on the one end, and then it's a rectangle on the other. So we're going to rearrange the equation that we know so that we're going to isolate the 1 so we can re-enter it in our volume equation. So you'll see in a second here. Those are V's. Lx squared. So now we're kind of going to do some substitution here, so that instead of using L, we have this, what L equals up here, so that we'll just get x values in there. So it'll be x squared, this is right down here, x squared 108 minus 4x. So now we can expand that out, so we'll give ourselves some more room here. 108 x squared minus 4x cubed. Now we can take the derivative of the volume equation, and that is what we wanted to do this whole time. And then we'll take the critical points. We can take out a 12x, 18 minus x. So that'll give us x values of 0 and 18. Sorry. Now we know that the x value of this is 18. And when we plug it back in, L plus 4x equals 108. Now we will plug in the 18 into the x value. So it'll be L plus 72 equals 108. So minus 72 from both sides. And L will equal 36. So now we know the dimensions of the box will be optimized. So the total volume will be optimized when x equals 18 and L equals 36.
So I'm going to show how to find the antiderivative, which is basically undoing finding the derivative. It's just the opposite of taking the derivative. It also becomes important later when trying to do the fundamental theorem of calculus by hand. So I'm just going to show a couple examples here. So one example would be, so say you have 4x cubed. So in the derivative, we would subtract the power by 1. But here we're going to add to the power by 1. So we're going to get x to the 4th. And since it's to the 4th, you bring 1/4 here. And the coefficient is 4. So you multiply those together. That gets you 1. So you're left with x to the 4th. And what you always have to have when taking the antiderivative is the constant. So you always have plus c in any antiderivative problem. And you do that because you don't know if there's a constant. The constant could be 0, which would just leave it as x to the 4th, but you don't know, so you always have to add plus c. Another example would be e to the x. Now, of course, the derivative of e to the x is just e to the x. So the antiderivative is the same. It's just e to the x, but it's again plus the constant c. So here's one more. Here's a trig identity. Secant squared of x. Well, this one is pretty simple because you would just take, this is the derivative of tan x. So you would just, so that would be the antiderivative because you're just going back. So that would be tan of x. And again, you have a constant. So that's how you find the antiderivative. So, Mr. Peller, that is what we've learned about the derivative up to this point. Just want to say thank you, and I hope you have a good special programs and a good spring break.
Thank you, Mr. Peller.
Okay, all right, bye.